Hello guys, welcome back again. So today we're going to discuss the advanced part of maximum power transfer theorem. That means whenever or what we do if we have a dependent source and how we solve it for maximum power transfer theorem. Okay, so here we are considering directly an example. So in this circuit we have to determine the value of load resistance RL for maximum power transfer and then determine the maximum power. So let me draw the circuit again. So this is our circuit. So in this circuit we have to determine the first we have to determine the Thevenin network. That means we have to determine VTH, we have to determine RTH, and the value of RL will be equals to RTH, right? So this we have to determine. So now whenever we have a dependent source, as we have discussed in our earlier class, for whenever we have solved for Thevenin and Norton theorem with dependent sources, we have discussed that. So in solving this type of network with dependent sources, the basic idea or basic logic behind solving is to determine first the value of VTH and VTH for Thevenin and ISC for Norton circuits. But in this circuits we cannot determine the value of RTH or RN using our normal rule for Thevenin or Norton circuit, because as per the normal rule what we have to do is we have to determine the equivalent resistance from the load terminal by replacing all the other sources which are independent by their internal resistances. So all the independent sources will be replaced by their internal resistances. But what about dependent sources? We cannot remove the dependent sources. Okay, so why we cannot remove the dependent sources? Because this is VTH, because the dependent sources are dependent on any particular current or voltage, so that current or voltage will not be zero. So it is why we cannot remove the dependent sources. So how to solve whenever we have a circuit with dependent sources? For that we have to determine both the values of VTH and ISC, and we have to determine RTH or RN equals to VTH divided by ISC. So by using this we can determine the value of the equivalent resistance, that is VTH or RN. So now in our case also we have to determine both VTH and ISC. So first let us consider removing the load. So we have to determine VTH. So we will be calculating VTH across this point. So this is plus, this is minus VTH. So in this circuit, as you can see here, we have a voltage source here which will be forming a super node sort of thing, because we do not have any resistance here. But at the same time also we can see these two terms, that is our 3 ampere and 4 ohm, they are forming a current source formation, and which we can convert into a voltage source. So if you convert this circuit into a voltage source, then the voltage source will come in series with the 4 ohm resistor. So this will get removed and the resistance value will remain same, since the current was in upward direction. So the source direction will also be like this, and the value will be 4 into 3 is 12 volts. Okay, so this will be a circuit. So now the circuit is simpler, so we can easily determine the value of this current I. So by applying KVL equation, so we have 12 minus 4I, then this will be plus 0.5 VTH minus 4I equals to 0. Now what is the value of this VTH? VTH voltage can also be determined by the voltage across this 4 ohm resistor. So VTH equals to 4I. So now we can replace 4I here, and from this we can solve the value of VTH, which will be, after solving, becoming as 8 volts. Okay, so we have got the value of VTH as 8 volts. Next we have to determine the value of ISC. So for determining the value of ISC, let us draw this circuit again, where we have already converted the source. So this is our circuit. Now what we can do here is, for determining ISC, we have to short circuit this terminal, and whatever current we get here is ISC, right? So now if we see it closely, then this short circuit path is in parallel with 4 ohm. So whenever current appears in this network, then it will not move through this 4 ohm, since we have a short circuit path which is not having any resistance. So all the current will be passing through this branch, right? So what we can do, we can eliminate this 4 ohm resistor, since there will be no current or very minimum amount of current will pass through this. Okay, so now our circuit is more simpler, and you can directly write down the KVL equation here. So for writing the KVL equation, now one more thing is there. Since we are short circuiting this terminal, then means the whole value of VTH will be equals to 0. Since the value of VTH equals to 0, so this term will also becoming 0. So we can eliminate this and replace this by a short circuit, right? So now what is the value of the current? So current value will be determined by ISC equals to nothing but 12 divided by 4. So we have only these two components here, which is given as 3 ampere. So now determining the value of RTH is VTH divided by ISC. So VTH we had 8 volt, and this is 3 ampere. So we have a resistance of 2.67 ohm. So we have obtained the Thevenin equivalent circuit. Now determining the maximum power. So maximum power we know is given by VTH square divided by 4 RTH. So this is H square by 4 into 2.67 ohm, and which will be coming as 5.999 watt, which we can also equalize to 6 watt. Now we have seen the power formula like this only, VTH square divided by 4 RTH, but the same equation we can also write it like this. The power is given by I square RL, right? I square RL. So P max is I square RL. So this is current I is IL. So the value of your current IL will be, so IL is from the Thevenin circuit. I am drawing the Thevenin circuit here. Please follow it from here only. So this is 8 volt, this is 2.67 ohm, and this is also 2.67 ohm. So IL is 8 divided by 2 into 2.67 ohm, which is coming as 1.5 ampere. So this IL will be 1.5 whole square into 2.67, which will be nothing but 6 watt, right? So both will be same. So we are getting the same answer using both the formula, right? So now what we have seen here, that for any circuit, yes, the circuit should be linear and bilateral as per our consideration in every theorems. So it should be linear and bilateral, and complex network can be converted into a simpler network, and that simpler network will be called as, or will be applicable for maximum power transfer when the source resistance is equals to the load resistance. So we have seen a numerical containing a dependent source, and we have applied maximum power transfer for determining the load resistance and then determining the value of the maximum power. So like this we can solve any numerical which contains a dependent source for maximum power transfer theorem. So I hope you have understood. So thank you for joining. So you can solve this type of numericals from any book that you can follow. So thank you for joining.